Okay, so let's continue. Now we talk about the basic polymer absorption onto the surface. Is what are the factors that influence polymer absorption onto the particle surface. Then let's talk about the steric stabilization of powder compact structure. Okay, the so-called polymer coverage ratio. We are looking at SiO2, the most typical ceramic, PZC or IEP, isoelectric point of 3 to 4, which means at 3 to 4, it's got very low surface charge, very low zeta potential. Okay, and this plot we look at it before. We are looking at what? The powder compact relative density versus fraction of polymer coverage on the particle surface. Okay. Another plot related is median pore radius. Pore radius. Like when powder come together, when sphere come together, there will always be some pores left between them. Pore radius average versus similarly the coverage. The coverage ratio of what? Polymers onto the ceramic surface. 0 means I have no polymer onto the ceramic powder. 1 means what? Kind of like close to monolayer or close, complete coverage of polymer over the ceramic surface. Okay, let's first focus on the pH equals 3.7 for both plot. pH equals 3.7, which means we are very close to what? IEP, zero charge. The surface, we don't consider electrostatic charge effect. Okay, so what we see is that as we increase the polymer coverage on surface, initially, what happened? The density becomes lower, or the porosity becomes higher. This region is what people call the so-called bridging effect. When my particle surface is just have a little bit of polymer on the surface, and then when two particles getting closer, actually the polymer on one particle and the polymer on the other particle have a tendency to so-called entangle each other. Hook. You imagine the polymer on one particle is like a chain, and the polymer on the other one is like another chain. And when they are coming to certain distance, they kind of like the chain and chain become interlocked a little bit, slightly interlocked, entangled a little bit. And that's causing so-called bridging flocculation, which means the particles, okay, come together, and then the flocculate or the agglomerate become larger, and as a result, they pack less dense. They pack less dense, or the pores become larger. Okay. On the other hand, if we continue to increase what? Polymer coverage. If we continue to increase polymer coverage to beyond roughly like 0.8, which means we are getting closer to full coverage, then we still have that entangle effect. We still have some of that entangle effect, but what is more dominating in this case would be the particles, they're full covered. Now they don't really want to come too close to each other. They don't really want to come too close to each other. I would get go back. They would pack more dense. Pack more dense means what? They pack dense. Actually, pack dense to closer to from this number is what? 58 decrease due to the so-called bridging flocculation, but then go back to 58 and then go back to 65 or even 66. For anyone who study crystallography, you would understand for balls to pack, if we imagine if the individual particle is a ball, the highest packing density for same sized ball is what? Yeah, close packing, right? Kind of like FCC or HCP close packing is up there. But then we are getting closer and closer to that. Not exact, but it's much higher than the initial 58. Going higher and higher, which means that actually the suspension become more stable. They don't randomly hook and then quickly drop. They repel each other more effectively and they have more time. It will take more time for them to precipitate, drop, and pack denser. And at the same time, the porosity become, not the porosity, the pore size become from here. I'm talking about here. Smaller and smaller. Why? Because it gives them time. It finds its the best place, lowest energy place. Okay, so this is what happens at pH 3.7. When we have very little charge, the polymers initially entangle, but then gradually have higher and higher coverage. They would have the steric stabilization. They would help the particles become stable and they would pack denser and give less pores. On the other hand, what we see is that by changing the pH, it's kind of even more effective. You see, like from this versus here, at pH 7.3, that means what? It's much more higher pH than this value, which means each of the particle is covered by a lot of hydroxy kind of group, negative charge, and then I would have so-called electrostatic stabilization. And even though I have no what polymers, they still give me the suspension is still stable. They would pack denser and give low pore size. Okay, so let's continue. And then about polymer molecular weight. Molecular weight would also impact the relative density. This one we are plotting relative density versus molecular weight for both pH 3.7 and 7.8. And we see for 3.7, which means we are zero charge, the higher the molecular weight, the higher the relative density. Okay, the higher the molecular weight, the higher the density. And if we also plot the corresponding pore size, the higher the molecular weight, the lower the pore size. This effect is not very effective, not very significant for when you have a lot of surface charge. For kind of like a zero surface charge is more effective. And the reason being, the higher the molecular weight, the larger the effective polymer molecule size or end-to-end distance. Because higher molecular weight means I have more chains, number of repeating unit, and as a result, the overall polymer appears larger. And if they are larger, they kind of like put them further away and better stabilized. Okay. On the other hand, if we have pH 3.7, it doesn't change it much because the electrostatic effect is sufficient and the polymer doesn't help too much. Okay. And then let's talk about solvent quality. We talk about solvent quality a little bit, how solvent quality or different solvent influence the polymer coverage on ceramics. Now let's look at the microstructure. This one is relative density for aluminum oxide packed with different polymer concentration. But here we're using two different types of solvent. One is more polar methanol, the other one is this mixed solvent. And here, of course, we are still having the so-called PVB as the polymer. Okay, with more polar solvent like methanol, the PVB packs doesn't really like the more polar solvent. PVB is a non-polar polymer molecule. It doesn't really like the solvent methanol, and as a result, the PVB polymer is in the solution, but it doesn't really stretch out. The PVB polymer doesn't really stretch out, and as a result, the so-called steric repulsion between different particles covered with PVB is not very effective. So as a result, the colloidal is less stable and they pack to lower relative density. But of course, as you increase the concentration, it packs slightly more denser. On the other hand, if we add less polar solvent, this MIBK solvent, less polar solvent into the methanol, we're making the solvent more and more nonpolar, which means the PVB now really get feeling at home with this solvent. Means what? PVB would stretch out more. And then as PVB stretch out more, which means in the PVB on the particle surface, they have relatively on average larger sizes. And the larger sizes means between different particles, they are more stable. They are more separated further away, they're more stable. And as a result, if I wait, they're going to pack denser. Eventually, they are going to pack, but they're going to pack denser. Okay. Okay.